Here's another quadratic equation. It's written in standard form. Remember, standard form is where we have the terms in descending powers of the variable, and we have all those terms on one side of the equation, and we have 0 on the other side of the equation. That's what we typically call standard form of a quadratic equation. The generic version of that looks like this. ax squared plus bx plus c equals 0, where a, b, and c are numbers. And those are called the coefficients of that equation. A is the coefficient of the squared term, B is the coefficient of the first power term, C is our constant term. So we have that equation in standard form. Unfortunately, this polynomial, this trinomial, is not factorable. So we can't solve this quadratic equation using our factoring method. Well, the beauty of the quadratic equation is mathematicians over the centuries have been able to develop a formula that we can use to solve any quadratic equation. And that formula simply revolves around us using these coefficients and putting them into an arithmetic expression, evaluating the arithmetic expression, and thus creating our solutions to the equation. This is what the expression looks like that we have to fill in the values from our equation. It says if you have a quadratic equation, for that quadratic equation, to find the solutions x, you take the opposite of the b coefficient plus or minus the square root of the square of the b coefficient minus 4 times the a times the c coefficient, all of that divided by 2 times the a coefficient. These, again, are just the coefficients. There's no variable. It wouldn't do me any good to put an x over here, because then I'd have an x on both sides, and that wouldn't be solving for x. So this formula, called the quadratic formula, is used to find solutions for a quadratic equation. All we simply do is identify the values of a, b, and c, plug them into that expression, and simplify that expression. So if I were going to apply the quadratic formula to this quadratic equation in order to solve it, I would first make sure it's in standard form, which it is. Then I would identify my coefficients. Remember, when no coefficient is written, the understood coefficient is 1. So the a coefficient here is 1. The b coefficient would be -6. And the c coefficient would be -3. Again, comparing this equation to the generic version of the standard form of a quadratic equation. So now I'm going to take those values of a, b, and c and plug them into this expression. This says take the opposite of whatever the b coefficient was. The opposite of -6 is +6. Then it says take the square root, that's plus or minus. And you say, what's that plus or minus mean? Well, the plus or minus means when you use the addition of this radical quantity, that's one solution. When you subtract the radical quantity, that's your other solution. Remember, quadratic equations typically have 2 solutions. So it's the opposite of b, the opposite of -6 is +6, plus or minus the square root of b squared. Well, the square of -6 would be 36. Minus 4 times the a coefficient, which is 1, times the c coefficient, which is -3. All of that quantity divided by 2 times the a coefficient. Notice it's the entire quantity divided by that 2a. And now I simplify this expression. I see what I can do in terms of simplifying this radical expression. 6 plus or minus the square root of 36. Now, isn't the minus here going to make plus? And 3 times 4 is 12. All of that over 2. So then x equals 6 plus or minus the square root of 48 over 2. Now, unfortunately, 48 is not one of my perfect square numbers. By that we mean, remember, a perfect square number is a number that when you take the square root, you get a whole number answer. So we have one of two things we can do. We can, if we want an approximation to our solutions, we can actually use our calculator to evaluate the square root of 48 and get approximate solutions. Or if we want exact solutions, we try to simplify that radical expression. We try to simplify the square root of 48. So let's look at that. Let's make our solutions in the exact form. So remember, you look at the square root of 48 and you ask yourself, is there a perfect square number that's a factor of 48? And in this case, 16 is the larger perfect square number that's a factor of 48. Isn't 16 times 3 48? So I can break apart the square root of 48 into the square root of 16 times the square root of 3. And then I can take the square root of 16. That's equal to 4. So the square root of 48 can be simplified to 4 times the square root of 3. So now my expression becomes this. X equals 6 plus or minus 4 times the square root of 3 over 2. See, I replaced the square root of 48 with its simplified form, 4 times the square root of 3. And now the last step that I would do would be to split those fractions and see if there's further simplifying that I can do. 6 divided by 2 is 3, and 4 divided by 2 is 2. You can never divide a number outside of a radical sign into a number that's under the radical sign. It's like, this number's in prison, this number's out of prison, they can't have anything to do with each other. But you can divide into a number that's not in prison, that's not under the radical sign. So here are our two solutions to that quadratic equation. 3 plus 2 times the square root of 3, and 3 minus 2 times the square root of 3. Those are what we call the exact solutions. If we wanted approximate solutions, then we could evaluate the square root of 3 here and perform the arithmetic to get approximate solutions. So this is an example of solving a quadratic equation by using the quadratic formula. This formula works for any kind of quadratic equation we might have.